Hello everyone, in this video, we will be presenting our research titled Kinetic and Thermodynamic Study on Catalytic Co-Pyrolysis of Tetra-Pax and Low-Density Polyethylene using the Thermogravimetric Analysis with Artificial Neural Network approach. Globally, environmental issues such as plastic waste accumulation and unsustainable packaging disposal are becoming increasingly serious. In Malaysia, approximately 39,000 tons of MSW generated daily. A significant portion of this comes from plastic packaging, which accounts for over 40% of total plastic consumption. However, less than 15% of plastic packaging waste is collected for recycling. In particular, 72.3% of Tetra-Pax packaging ends up as waste due to its complex composition materials. Currently, the common disposal method of this material are usually landfilling or open burning, which will significantly contribute to environmental pollution and greenhouse gas emission. How do we alleviate this issue? One promising solution is pyrolysis, a thermal decomposition process carried out in an inert atmosphere. Pyrolysis process is able to convert waste materials into useful products such as biochar, bio-oil, and syngas. By adding catalyst, its efficiency can be improved by reducing the required temperature, enhance the quality, and altering the composition of the pyrolysis product. This method can also enhance the United Nations SDG goal, which are SDG 7, 12, and 13. Moreover, the pyrolysis of Tetra-Pax and LDPE can bring market opportunities to the industry. Tetra-Pax and LDPE are under-recycled due to the complex multi-layer of these materials. Co-pyrolysis offers a solution in chemical recycling technologies which can meet extended producer responsibility and reduce landfill dependency. The fuel and chemical industry are able to produce bio-oil for fuels, syngas for power generation, and aromatics for petrochemicals. Carbon credits and green finance can also be accessed for companies utilizing this technology. Machine learning is one of the technological advancements that enable the Industrial Revolution 4.0 to take root. Hence, in order to reduce the time required in data interpretation, artificial neural network is an ideal approach. Artificial neural networks are inspired by the human brain and is used to determine complex and multitudinous relationships. It is able to recognize the pattern and trend of the data instantly. ANN consists of three neuron layers, which are input layer, hidden layer, and output layer, and it is widely used in various applications such as self-driving car, financial market prediction, facial recognition, and prediction of possible outcomes for industrial processes. Our methodology for this research consists of four main steps: sample preparation, thermogravimetric analysis, ANN prediction, and kinetic and thermodynamic analysis. The material used were Tetra-Pax and LDPE. The mixture ratio was set at 80:20. Then calcium oxide catalyst was added into the sample with a sample to catalyst ratio of 10:1. Four different samples including co-pyrolysis of Tetra-Pax and LDPE with and without the catalyst were tested. Next, thermogravimetric analysis (TGA) was conducted using the thermogravimetric analyzer. Approximately 10 mg of the sample was placed on the ceramic crucible. Then, the sample was heated at the temperature range of 50 to 900 degrees Celsius under 5 different heating rates with a nitrogen gas flow rate of 100 ml per minute. The output data obtained were wet loss percentage with respect to temperature and derivative wet loss percentage with respect to time, and then thermogravimetric and derivative thermogravimetric curve were plotted. After that, the TGA data obtained was then used for ANN prediction. The training function was set as Levenberg-Marquardt with 4 different transfer functions. Heating rate and temperature were used as the input data, while the output data was set as the wet loss percentage. Trial and error were used to determine the lowest mean square error in which neurons number for further kinetic and thermodynamic analysis. Lastly, the kinetic analysis was conducted using the model-free methods, which were Kissinger-Akahira-Sunos, fragment, and starry model. Kinetic plots were plotted based on the equation with the conversion of 0.1 to 0.9. Then, the gradient of the plot was used to determine the activation energy, while the y-intercept was used to determine the Arrhenius value. Lastly, the kinetic data obtained was used to calculate the thermodynamic parameters. From the DTG curve, we can observe that Tetra-Pax has undergone 4 significant stages, which are the moisture removal in stage 1, cardboard degradation in stage 2, polyethylene decomposition in stage 3, and second stage cardboard degradation in stage 4. As for LDPE, only one significant peak is observed, which is the occurrence of the LDPE decomposition at the temperature of 400 to 550 degrees Celsius. What happens if we mix both Tetra-Pax and LDPE together? From the DTG curve, we can observe that it is the assimilation of the combination of DTG curve for Tetra-Pax and LDPE. By adding calcium oxide catalyst, it is observed that the maximum degradation rate decreased, indicating that the catalyst used is suitable to enhance the pyrolysis rate and lower the activation energy of the pyrolysis process. Was the ANN model predicted? The ANN was designed with two hidden layers as the optimal architecture for co-pyrolysis. The major criterion to determine the most effective network topology is based on the highest regression value, which is also the lowest mean square error. From our analysis, we determined that TT and LL transfer function were chosen to be used for further analysis due to the lowest mean square error obtained. From the prediction, we can also see that both transfer functions actually show good agreement between the experimental and predicted data for all samples. For the kinetic analysis, kinetic plots were plotted for every sample corresponding to different conversion factors from 0.1 to 0.9. The best fit of the kinetic plot was used to determine the gradient and y-intercept to obtain the activation energy and Arrhenius factor respectively. Regression value was also obtained to determine the accuracy of the kinetic data analyzed. From the table, it can be seen that the LL transfer function has higher regression value, indicating that it has higher accuracy. This has been proven in literature, which log-seq transfer function has better performance than the time-seq transfer function. Therefore, the experimental data and LL transfer function predicted data were used to further analyze the kinetic and thermodynamic study. In the activation energy, the KS model is found to have lowest percentage error among all the proposed kinetic model. This indicates that KS has better accuracy and hence the thermodynamic study will be conducted based on the kinetic data obtained from the KS model. It can also be observed that the presence of calcium oxide catalyst has actually decreased the activation energy by 8 to 10%. In the thermodynamic study, it is found that the Arrhenius factor value is in a vast range due to its complicated chemical reaction. Moreover, this process is an endothermic reaction as the enthalpy change obtained is in positive value. The Gibbs free energy change has higher value and this indicates that the system absorbs more energy. As for the entropy change, it is less than 0.5 kJ per mole, indicating that the solid substances have undergone both physical and chemical reaction that brought it closer to its thermodynamic equilibrium state. Why are kinetic and thermodynamic analysis important? The kinetic and thermodynamic analysis can be used in the industry for process optimization, reactor design and scale-up, process simulation, as well as cost control and energy efficiency. In conclusion, artificial neural network is able to predict the thermogravimetric curve accurately. Calcium oxide is a suitable catalyst that can be used in reducing the activation energy by 8 to 10%. In the kinetic analysis, KAS model is the most accurate model due to the lowest percentage error obtained. The catalytic co-pyrolysis of Tetra-Pax and LDPE is an endothermic reaction due to the positive enthalpy change obtained. The entropy change is also less than 0.5 kJ per mole Kelvin, indicating that solid substances have undergone physical and chemical reaction that brought it nearer to its thermodynamic equilibrium state. That's all for my presentation. Thank you for listening.